Assalamu alaikum, dear students. Okay, last time we were discussing uniform continuity, and with the help of a few examples, we have seen that a uniformly continuous function is always continuous. However, a continuous function may not be uniformly continuous. So, there is a natural question: can you find all those functions which are continuous as well as uniformly continuous? So, for this question, we have a theorem, and this theorem is very well known theorem. This is called Uniform Continuity Theorem. So, today I am going to prove this theorem, Uniform Continuity Theorem. And before this, I want to tell you one more criterion, which is non-uniform criterion. As last time we have seen that if a function is not uniformly continuous, then there must be at least one epsilon naught positive such that fx minus fy mod is greater than or equal to epsilon naught, even though x minus y mod is less than delta for every positive delta. That was the non-uniform criterion we have discussed last time. And instead of using x and y, we can choose sequences x and y. So this criterion is same. So instead of two arbitrary point x and y, we are choosing two arbitrary sequences from the domain which are satisfying the criterion, as we have elaborated in our last lecture. Okay, so what is this? A non-uniform continuity criterion. A function f from a to r, where a is the domain, is not uniformly continuous if and only if there exists at least one epsilon naught. So the idea is to search such an epsilon naught. So there exists at least one epsilon naught and the two sequences x and y in your domain in A, such that fxn minus fyn is greater than or equal to epsilon naught, even though xn minus yn mod is less than delta for every positive delta. Okay, so this is another criterion we have established through the last non-uniform criterion. Instead of writing x, y, we are choosing two sequences because we will use our non-uniform criterion to prove uniform continuity theorem. Okay. So you can also apply this criterion to show that a given function is not uniformly continuous. Like I have one example. Say you have fx is equal to 1 over x on 0 infinity, it's your domain. You must have to choose some epsilon naught and some and the two sequences xn and yn, such that xn and yn mod is less than delta for every positive delta. Of course, we are emphasizing on a smaller value, but fxn minus fyn is equal to or greater than epsilon naught. So for this, let epsilon naught is equal to 1 and choose two sequences in this domain, and take two sequences. You can choose 1 over n, this is a sequence, and 1 over n plus 1 in 0 infinity. Okay, you can check, yes, here n is a natural number where n belong to capital N, where n is a natural number. You see that if you substitute any natural number, then 1 over n, this sequence is here in this domain. And also 1 over n plus 1 is a similar sequence. This is also in the sequence, which is a sequence in 0 infinity. So I have chosen epsilon naught is equal to 1, and the two sequences 1 over n and 1 over n plus 1. Now I need to show that f of this sequence, you can say this sequence is xn, say this is equal to xn, right? And say this is equal to yn. So you can choose two sequences, xn is equal to 1 over n and yn is equal to 1 over n plus 1, right? So I have to show that fxn minus fyn greater than or equal to this epsilon naught. I have chosen epsilon naught is equal to 1. So let's see. Okay, we see that here xn is equal to tends to 0 as n tends to infinity, and yn is also tends to, this was 1 over n and this was 1 over n plus 1. This also tends to 0 as n tends to infinity. So both the sequences are converging to 0, and also xn plus yn, xn minus yn, this is less than or equal to xn plus yn, and this tends to 0 plus 0, which is equal to 0, which is less than delta for every delta positive. That is xn minus yn mod is less than delta. However, we see that so here you see that 0 is the limit of this sequence, also 0 is the limit of this sequence. Then you can use the definition. When n tends to infinity, 0 becomes the limit of both the sequences. Now, however, fxn minus fyn, what is this? What is fxn? This is 1 over 1 over n. 1 over 1 over n minus 1 over 1 over n plus 1. So what this? This is n minus n plus 1, and you are getting 1, which is equal to epsilon naught, which is equal to 1, and which is greater than or equal to epsilon naught. Yes, we have seen the definition that fxn minus fyn is greater than or equal to epsilon naught. However, even though xn minus yn less than delta for every delta positive. Yes, this function fx is equal to 1 over x is in fact not uniformly continuous in our domain 0 infinity. Okay. Okay, I have another example. You can have another example. Take another example. Fx is equal to sine 1 over x on 0, 1 is not uniformly continuous. It's not uniformly continuous. Okay, let epsilon naught is equal to 1. Again, you choose two sequences in this domain so that xn minus yn mod is less than delta, right? We choose two sequences xn and yn with xn is equal to, I'm choosing 1 over n minus 1 by 2 into pi, and yn is equal to 1 over 3 xn, and what is xn? This is 1 by 3 into 1 over n minus 1 by 2 into pi, or you can say that 1 by 3 into n minus 1 by 2 into pi. So here you see, for you take xn minus yn, we need to see that what is 1 over n minus 1 by 2 into pi minus 1 over 3 into n minus 1 by 2 into pi. Okay, what is this? If you simplify, this is 1 over n minus 1 by 2 into pi into 1 minus 1 by 3. This is equal to 2 by 3 into n minus 1 by 2 into pi, say, and this is less than delta. Say this is less than delta. Of course, you have chosen delta is a very small number. So whatever delta you are choosing, you can find a natural number, and here n is a natural number, is a very large natural number, so that this value becomes lesser than delta. So that's why it's natural. There is no problem, because here we are using small n as a natural number. So whatever the delta, positive, however small you are choosing, you can always find a natural number, a very large natural number, so that this number will become less than delta. So there is no problem, right, for every delta. As since we can find n belong to capital N for every delta positive, however small. Yes, this is absolutely true, that whatever the delta value, however small you are choosing, we can find a natural number, a very large natural number, so that this value will become lesser than delta. So that's why you can say that xn minus yn mod is less than delta for every small positive delta value, right? Since we can find small n, a natural number, of course a large natural number, enough large to make this number is lesser than delta, where delta is your pre-assigned, whatever delta and however small it is, we are not concerned. We can have this relation. Also you can establish this relation with the help of Archimedean property. There is no problem. Okay, but we need to check that what happened with fxn minus fyn, right? We need to show that fxn minus fyn mod is greater than or equal to epsilon naught. Okay. So now fxn minus fyn, this is equal to, in fact, sine of 1 over, is your value, 1 over n minus 1 by 2 into pi minus sine of 1 over 1 by 3 into n minus 1 by 2 into pi, this one, and this is equal to sine of n minus 1 by 2 into pi minus sine of 3 into n minus 1 by 2 into pi. Yes, it is. And then this becomes this is equal to sine of n pi minus pi by 2, and this is equal to minus sine of 3n pi minus 3 pi by 2. Now you can apply simple formulas of sine alpha minus beta. This sine alpha cos beta minus cos alpha sine beta. You will get sine alpha is 0, and I can write sine n pi sine alpha cos beta cos pi by 2 minus cos n pi cos alpha sine beta sine pi by 2 minus, again we are using the same formula, sine 3n pi cos 3 pi by 2 minus cos 3n pi sine 3 pi by 2. Okay. So if you see, this is sine n pi is 0, cos pi by 2 0, this is 1, this is 0, this is 0, this one is minus 1. So now substituting our values, you see that this is equal to minus cos pi, this is minus cos n pi, and then minus this minus and minus, this is plus, and cos 3n pi into sine pi by 2 is minus 1. Right, so this is equal to, in fact, this is minus from either side in every term, so this minus can be neglected due to absolute value. So you can write cos of n pi plus cos of 3n pi, and this is equal to minus 1 power n plus minus 1 power 3n. Right. Now whatever the value of n is, if n is odd, then this is minus 1 and minus 1. Okay. We are getting answers 2. If n is even, then this is 1 and this is also 1. Anyways, this is equal to, which is greater than 1, which was epsilon naught. Right. So we have established what does it mean? Therefore, fxn minus fyn mod is greater than or equal to epsilon naught, even though xn minus yn mod is less than delta for xn and yn in 0, 1. So yes, we have seen that you can choose two sequences xn and yn from this domain so that xn minus yn mod is less than delta. However, fxn minus fyn mod is greater than or equal to epsilon naught. Yes, this means that sine 1 over x on this domain is not uniformly continuous. Okay. So yes, now we can understand this non-uniform criterion, that you can say that a function f is not uniformly continuous if and only if you can always find there exists at least one epsilon naught positive and the two sequences from your domain xn and yn such that if xn minus fyn mod is greater than or equal to epsilon naught, even though your the deviation, absolute deviation of the domain values is less than delta. That is xn minus yn mod is less than delta. Okay, now the next idea is the uniform continuity theorem. What is that theorem? Let here we have to let I is equal to AB, a closed and bounded interval if f is continuous on I, then it is uniformly continuous on I. Okay, this is a very simple result. If your function is uniformly continuous on a closed and bounded interval, you know that we call this closed and bounded interval as compact as well. So this theorem can also be stated as if function f is continuous on a compact set, then it is uniformly continuous, right? So that was a natural question. Since you have seen that not every continuous function is uniformly continuous, so there was a natural quest and a natural question that can you find all those functions which are continuous as well as they are uniformly continuous? So the answer is this theorem. If your function is continuous on a closed and bounded interval, means to say if your function is continuous on a compact set, then we can say that, then we say that it is also uniformly continuous therein, right? So proof is, proof. So we will be using our last criterion for not uniform continuity. We will say that suppose this function is continuous on your closed interval AB, but not uniformly continuous. For if it is not uniformly continuous, then you can always find two sequences and at least one epsilon naught, so that xn minus yn mod is less than delta, while fxn minus fyn mod is greater than or equal to epsilon naught, right? So suppose f is continuous on I, but it is not uniformly continuous on I, then by non uniform criterion of continuity, there exists at least one epsilon naught positive and the two sequences xn and yn such that fxn minus fyn mod is greater than or equal to epsilon naught, even though xn minus yn mod is less than delta. Say this one is number 1. Okay, I'm doing nothing. We have discussed a non-uniform criterion of continuity And I am saying that suppose your function is continuous on I, however, it is not uniformly continuous. If it is not uniformly continuous, then by non-uniform criterion of continuity, you can always find at least one such an epsilon naught, and the sequence is xn and yn, such that these conditions are satisfied. Okay. Now, what happened if you are doing this? Say, uh, for sake of convenience, I can use xn minus yn is less than 1 over n, which is equal to delta. Say, which is less than delta as well. This is possible. You can always choose. You can always choose a natural number, since for n belong to capital N. You can always find some natural number n, so that 1 over n is less than delta, because n is a natural number. So whatever the delta you are choosing, as I have explained in last example, you can always find a larger value of this small n, a larger natural number, so that 1 over n must be less than delta. So I am choosing, for sake of convenience, xn minus yn is less than 1 over n, right? Okay, now I am using my previous idea of boundedness and closeness, since xn is a sequence in, since xn is in I is equal to AB, and I is bounded. So xn is the bounded sequence in I. And you know by Bolzano-Weierstrass theorem that every bounded sequence has a convergent subsequence. Then by Bolzano-Weierstrass theorem. Okay, for sake of convenience, I am using BWT, so Bolzano-Weierstrass theorem. Then, so xn is a bounded sequence in I. Then by Bolzano-Weierstrass theorem, xn has a subsequence. It has a convergent subsequence, say xn k, right? So let limit, or you can say that xn k tends to z. Okay, since I is bounded and xn is a sequence in I, so xn also a bounded sequence, and we know by Bolzano theorem that every bounded sequence has a convergent subsequence. That's why you have supposed that xnk is a convergent subsequence of xn, and say xnk converging to z. Also your interval is closed. When I am saying that a set is closed, this always means that this set is containing all of its limit points. So if a set is closed, whenever you take a sequence in that set, it must be convergent. It must be convergent. So you know convergence is with respect to space, means so that its limit is also an element of your set AB. But I is equal to AB is closed as well, hence this Z belong to AB. Okay, so I have shown that our sequence, subsequence x and k is in AB and also converging to a point of AB. Now if I can show that the subsequence of yn, which is yn k, is also converging to this z, then it would be so easy for us to establish negation against the definition of continuity. So let's see. Now my target is to show that there is a subsequence of yn as well, which is also converging to this z, right? Okay. Let y and k be a subsequence of yn. You know, this is also a convergent subsequence because you have taken yn a sequence in I. Yn is also a sequence in I, and yn is also bounded, so it has a convergent subsequence. Let this be y and k. You can argue by the same, using the same lines, but no, it is obvious that y and k is a convergent subsequence of yn. But I have to show that this convergent subsequence is also converging to z. Okay. So let y and k be a subsequence of yn, which is also convergent, which is also, I mean say y and k is also convergent, is also convergent, is also a convergent subsequence of yn. Now we see that y and k minus z, my target is to show that y and k is also converging to 0. If this is the case, then it would be so easy to establish negation against the definition of continuity as well, right? So y and k minus, see, you can write this is y and k minus x and k plus x and k minus z, and here this is less than equal to, this is in fact or you can write y and k minus z is less than equal to y and k minus x and k plus x and k minus z. Okay. You know that you have assumed that xn minus yn mod is less than 1 over n. So these are the subsequences of xn and yn. Since the supersequences, the deviation between supersequences xn minus yn is less than 1 over n, so the subsequential terms are in fact the terms of these sequences as well. So because must satisfy this condition. So that's why this must be less than 1 over n plus, you know that x and k is converging to z. So you may assume that this is maybe less than some epsilon by definition of convergence. So you choose where you, as x and k minus converging to z. So for epsilon positive, you can choose a natural number so that x and k minus z mod is less than epsilon. This is our previous definition. You can watch my lectures on the convergence of a sequence to understand the definition. So that's why this is trivial, that x and k minus z is less than epsilon for some natural number, you know, nk is greater than or equal to n star. Okay, so say this is equal to epsilon dash. Say, what does it mean? Y and k is also less than epsilon dash for the same natural number, where nk is greater than or equal to n star. So you can say that this is also less than epsilon dash for some n k is greater than or equal to n star by using the definition of convergence of a sequence. Hence, this means that y and k is also converging to z, right? But then, since f is continuous, so by a sequential criterion of continuity, then by sequential criterion of continuity, since f is continuous, you have supposed that your function is continuous. So then by sequential criterion of continuity, fx and k minus fy and k would be equal to, this, if x and k tends to z, then fx and k tends to f of z. This is f of z minus f of z, and this tends to, this is less than epsilon naught. A contradiction? Against 1. Okay. Then by a sequential criterion of continuity, you have seen that your fx and k tends to f of z, your f of y and k tends to f of z, because x and k, you have assumed that x and k is converging to z, and you have established that y and k converging to z. Then by the sequential criterion of continuity, it is so easy that the corresponding values of their sequences, that fx and k must be converging to f of z, and fy and k must be converging to f of z as well, so that fx and k minus f and k would be equal to f of z minus f of z converging to, or you can say that this must be converging to f of z minus f of z, that would be less than epsilon naught. So in fact, this converging to 0, this is converging to 0, which is less than epsilon naught, because epsilon naught was a positive number. So what we have established, so I have established that x and k converging to z, y and k converging to z, and f is continuous. So by sequential criterion of continuity, fx and k tends to f of z, and f of y and k tends to f of z. Okay, this is the major thing that we are using. Since you have established that x and k tends to z, you have assumed that since x and k was xn was bounded and it has a convergent subsequence, and you have assumed that xn has a convergent subsequence x and k, and suppose this is converging to z, and we have established that y and k is also converging to z. Since f is continuous on I, f is continuous on I, so by sequential criterion of continuity, this is so easy that fx and k converging to f of z, and fy and k converging to f of z. If this is the case, then of course fx and k minus f and k converging to f of z minus f of z, which is tends to 0, which is less than epsilon naught. So consequently, we have established that is fx and k minus fy and k mod is greater than or equal to epsilon naught. A contradiction against 1. So what was your 1? In equation 1, you have established that fxn minus fyn mod is greater than or equal to epsilon naught. You can choose, and this is since fxn minus fyn are following this condition, so because their subsequences fxn k minus fyn k must also satisfy this condition. But on the other hand, what you have established, you have established this is less than epsilon naught, this is less than epsilon naught. You have established that this is less than epsilon naught, but you have assumed that this is greater than or equal to epsilon naught, right? So that's why you have a contradiction against 1. So this means that why you have created such a contradiction, because you have assumed that your function is not uniformly continuous. This means that our previous supposition was wrong. Okay. Hence, our previous supposition is wrong. Therefore, f is uniformly continuous on I. Okay. Now I want to summarize this theorem again. You know the idea of non-uniform continuity, because I have defined whenever your function is not uniformly continuous, if and only if there always exists at least one epsilon naught and the two sequences xn and yn, so that fxn minus fyn mod is greater than or equal to epsilon naught, even though xn minus yn mod is less than delta. So you have supposed that your function is continuous but not uniformly continuous. So that's why you can apply the non-uniform criterion. Now since xn is in I and I is closed, is compact, that is bounded as well. So by Weierstrass theorem, Bolzano-Weierstrass theorem, this must has a convergent subsequence. Let it be x and k, and also this is converging to Z. Since yn is also in your domain I, so yn also has a convergent subsequence. Let it be yn k, and my target is to show that yn k is also converging to y. Soon after I established that yn k is also converging to Z, you have xn k, fxn k minus fyn k converging to 0. Since f is continuous, so by using the sequential criterion of continuity, this is so easy to establish, which would be a contradiction, as you have supposed that you have established this is less than epsilon, but this is against the contradiction. Hence f is our previous supposition is wrong and f is uniformly continuous. Okay, now with these remarks, I have completed today's lecture. Inshallah, next time we will have more theorems on uniform continuity. Thank you very much. Allah Hafiz.